Does anybody have homework questions before we begin? I actually had gotten emailed about 6 questions, so I'll make a separate video later on and upload that. And then if you're stuck over the weekend, you can look at that video, okay? Hopefully it'll be a question that you have if you do get stuck. We're going to look at the Mandelbrot and Julia sets today. Here's the Mandelbrot set. If you remember, we talked about how dense the numbers are on the number line, that between every 2 numbers there's another number. Well, we find that here, and that's why they're able to keep zooming in. So they keep zooming in, and fractals are self-similar at a number of different levels. So that's what we'll see going on. We'll see some self-similarity. And we'll see that we can keep zooming in because between any 2 numbers like 1.2 and 1.3, there's another number, 1.25. And between 1.2 and 1.25, there's another number, 1.23, for example. So our numbers are dense, and we can keep zooming in and zooming in and zooming in. And that's what's going on in the Mandelbrot set. So we can keep watching this for a long time. If you want, you can put your cat in front of it and watch her go kind of starry-eyed. Okay? But we'll go ahead and see, where does this Mandelbrot set come from?
The screens are on. The screen's not on.
Oh, you didn't get to see that. Okay, we'll do it again then. Here, from the beginning. Online students, sorry. There we go. Online students did have it going, so they're going to get to see it again. Can you see the color there? Is it even showing up? Maybe I'll shut a couple of curtains in the back. Okay. So these are beautiful fractals. They come from the Julia set. So we're looking at the Mandelbrot set right now. The Julia set was imagined and created by Julia in the 1920s when he did not have any way to actually visualize the set. And then Mandelbrot came along in the 70s and 80s and took all of Julia's sets and put them together, and the combination of all the Julia sets that meet a certain criteria make the Mandelbrot set. So let's go ahead and see where did this come from. So your author starts this section out with a question about what is the story behind this picture, and so that's what we're going to investigate. Remember, we've been looking at fractals. There's not actually a precise definition of fractals, which is curious because in math we have precise definitions for almost everything, but here's fractals that we don't. So we'll say informally that fractals are infinitely complex patterns that are self-similar across different scales. And they are created by repeating a simple process over and over in an ongoing feedback loop. So we looked at one way to make fractals where we took a shape and shrunk it down and put it in place, and took a shape and shrunk it down and put it in place. Today we're looking at a different way. So to get an idea for how we make the Mandelbrot set, we start with Julia sets. Here's a picture of a few Julia sets from your textbook. So, to get to the Julia sets, so Julia noticed that numbers, when they're squared, can get bigger or smaller. So if you take a fraction, for example, smaller than 1, like a half, and square it, you get 1/2 times 1/2, which is a fourth. Well, a half is one of 2 slices, and a fourth is one of 4 slices of a circle. So the fourth is smaller. And then you can take the 1/4 and square that, and that gives you an even smaller number, 1/16, so a 16th of a whole. And you can continue this process, you take the 1/16 and square that, and that gets even a smaller number. So some numbers, as you square them and square them and square them, they get littler and littler and littler, but some numbers get larger when you square them. So numbers larger than 1, they get bigger when you square them. So 2 squared is 4, for example. 4 squared is 16. Then I square 16, I get 256. Well, that's pretty evident with the numbers that are numbers you're used to working with, but it's also true with the complex numbers. So this Julia sets actually come from the complex numbers. So complex numbers might have an I in them. Does anybody remember from algebra class what the square root of -1 is named? That's where my husband quit algebra. He's like, I don't do this. That's it. That's where his math career ended.
Impossible numbers?
Yeah, impossible, or actually they're imaginary. So they have a name, I, but you can think of them as impossible because you can't really square a number and get a -1, and so they have that name imaginary. But often mathematicians go through the realm of imaginary numbers and come back out with real answers to real problems. At any rate, what Julia did with these is all of the complex numbers can be written as a plus bi. For example, 2 minus 3i, or 5 plus 6i, or -0.2 plus 0i. In fact, -0.2 plus 0i is just a regular old number on the number line, -0.2. So all the numbers that you know are actually complex numbers, but Julia took the ones that you know and included those that have an I in them and made the Julia sets. So what we're going to need to be able to do is see how these are plotted. Recall how you used to plot points in algebra class. So for example, if you were plotting the point 2, 3, the 2 would be the x and the 3 would be the y. And then you had the horizontal axis, that was the x-axis, and the vertical axis, that was the y-axis. And then you went to the right was positive values, and to the left was negative for the x-coordinate. And then the up was positive for the y's, and down was negative. So if you had the point 2, 3, the 2 would mean 2 in the horizontal direction, and the 3 means 3 in the vertical direction. Or how about if we plot the point -2, -1? So -2, we go left 2, because that's the first number, and down 1 for -1. So the first number is where you go left or right. The second number is where you go up or down. Well, it turns out you can plot complex numbers as well by using the same idea. So let's go ahead and look at the complex plane. So the Julia set and the Mandelbrot set are both plotted in the complex plane. So it's just like the Cartesian plane, except the vertical axis stands for the I coordinate. Okay. So if we wanted to plot the number 3 minus 2i, the 3 would be on the horizontal axis, and then the -2 would be on the vertical axis. So you go right 3 and down 2. You have 3 minus 2i. Or suppose we take -1 plus 4i. Okay, so the negative 1 is the part without the I, so you go left 1 and up 4. So all the points that we see plotted on the Julia set and the Mandelbrot set are plotted in the complex plane in this way. We could have something with a 0. How about 5 plus 0i? So we'd have 5 plus 0i right here. Okay, so you wouldn't go up or down at all. Here, I'll give you a point to plot. Make sure you're getting the hang of this. Can you go ahead and plot negative 2 minus 3i on the complex plane, please? So you should have gone left 2 and then down 3. Whoops, I put parentheses. Anybody want to try another one of those? Anybody have any questions? Okay, so all of our points in the complex plane have a Julia set associated with them. There is a Julia set to go with every complex number. So each of these complex numbers we'll call C. Okay, so 2 plus 3i would be one complex number, C. 5 minus 2i would be another complex number called C. So there's a Julia set to go with every one of these complex numbers. And the way that you make the Julia set to make the Julia set, you first pick C. So you pick some complex number C, and then take for every complex number, for every single complex number, you're going to square it and then add C. So you take a complex number and you square it and you add C, and that gives you a new number. You repeat that. So you keep doing that. So I was doing that with these fractions and with these whole numbers earlier. I was just taking a number and squaring it, and then taking the result and squaring it. So I wasn't adding a number in, but I was using the result. 1/2 squared was 1/4, and then I was taking the 1/4 and squaring it. And then I was taking the 1/16 and squaring it. So we're taking a complex number, squaring it and adding C, and then take that result and square it and add C. Well, what happens then is that the result, you continue on like this, and the result either gets smaller or gets bigger. Just like with those numbers I used. Okay, the result either gets smaller or it gets bigger. So if it gets smaller, then that's a number that's going to be colored black.
So how do you define the different changes?
And you include it in the Julia set. If it gets bigger, then it's not going to be black. It's not going to be included. So every number in the complex plane is associated with the Julia set. Here, we'll look at another Julia set. Okay. So all these black points, well, let's look at ones that have a number associated with them. Okay, so here's some Julia sets that have numbers associated with them. Here we have negative 0.3 plus 0.03i. Negative 0.3 plus 0.03i. So this, any of the points that are black, I'll just pick this point. This point is black. That means it was squared and then added negative 0.3 plus 0.03i, and that result was squared, and added negative 0.3 plus 0.03i, and again and again and again. And as that was happening, the result went and got smaller and smaller and smaller. It didn't get bigger and bigger and bigger. And so that's why this point is black. It was included. Whereas if I pick a point out here, this is all plotted in the complex plane. So if I pick a point out here and square it and add negative 0.3 plus 0.03i, and take that answer and square it and add negative 0.3 plus 0.3i, and continue on with that, then that gets big. It gets real big. So we could spend time squaring complex numbers and adding I, but I think that's a little mathier than we want to do. I brought an app that if you have an Apple product, you can download, and it will do these Julia sets for you. It's really a nice fractal generator. See if it looks better with the light on. No, I don't think so. Okay, so this is called the Fractal Factory, and it's not coming in well, and I'm not sure why. That's not working. I think my screen is too bright for this. Let's see if I move this somewhere. My screen protector is acting like a mirror. Does anybody have that going on? Did anybody get theirs to go? A fractal generator? Well, it takes like 5 minutes to get an OtterBox off, but maybe I can get it off quicker. Usually when I want the OtterBox off, I take it down to the IT desk because it's hard. It's hard to get it off.
Wait, is there a payment in this?
No, it should be free, and it's called the Fractal Factory. Maybe when I have an image on, it won't be so bad. Oh yeah, okay, once the image is on, it's okay. So here's an image of one of the Julia sets. You're able to enter in the numbers here for your Julia set. So this one is at 0.32 plus 0.44i. I don't know if that's showing up very well. There, it shows a little better. 0.33 plus 0.44i. So these black points are included in the Julia set that goes with 0.33 plus 0.44i, because if you take the complex number, that's where I'm pointing with my pen on the black spot here, you take that complex number, you square it, you add 0.33 plus 0.44i, and keep doing that, square the result, add 0.33 plus 0.44i, the result gets smaller and smaller. Whereas if I pick a number out here and square it and add, and square it and add, and square it and add, I get something too big. The colors, the red, green, yellow, purple, those are points that do go shooting off. They get larger and larger, but the colors are how fast they get larger and larger. So depending on how fast they get bigger and bigger, they go off. So you can pick, say we just put 0 in here. And 0, put 0 here. That's just a circle. So the simplest Julia set is with the number 0, and it's just a circle. And we can get more and more complicated from there. We could have 0 plus 1i. So that's more interesting. So the Julia sets then are all those black points, because when you square them and add their complex number c, they get smaller and smaller. Now the Mandelbrot set, we still haven't got to. What is the Mandelbrot set? So here's a picture of the Mandelbrot set circled by Julia sets. The Mandelbrot set is all of the complex numbers whose Julia sets are connected. So let's write that down. So, well, we'll write that down in a minute. So actually it'll be easier to understand if we write it down. The Mandelbrot set is the collection of all of the complex numbers whose Julia sets are connected. Maybe I better show you what I mean by connected. So let's look at that app again and find some Julia sets that are connected and some Julia sets that are not connected. So here's a Julia set that's all connected, meaning you can get from any black spot to any other black spot without leaving the black spots. Okay, so this is a connected Julia set. It's like a distorted circle because you can get from any black spot to another black spot without leaving the black area. Here's a Julia set that's not connected. You can't get from every black spot to every other black spot without leaving the black spots. So this number for this disconnected Julia set is 0 plus 0.89i. Actually 0.90. 0.90i. 0 plus 0.90i would not be in the Mandelbrot set because its Julia set is disconnected. Whereas this Julia set goes with the number 0 plus 0.5i. So 0 plus 0.5i would be in the Mandelbrot set. It would be a black point in the Mandelbrot set because this is a connected Julia set. So every complex number goes with a Julia set, and then the Mandelbrot set looks at all the Julia sets, and if their Julia set is connected, well, then that's a number that's in the Mandelbrot set, a point that's black. If their Julia set is not connected, then they are not in the Mandelbrot set. So I have another software program that helps with that. Maybe I should make it more clear if I can. Okay, so there is a Julia set to go with every complex number. Okay, so there's a Julia set to go with every complex number, and we wrote that down once before. The Julia set is either connected so then it probably looks like some kind of distorted circle, or not connected. So it may look like something like that. So the complex number is in, we'll call it C. C. C is in the Mandelbrot set if the set's connected. Or if it's not connected, C is not in the Mandelbrot set. Well, there's a very nice generator for Julia sets that goes right with the Mandelbrot set. So if you have your phone or some other device that you can load a website on, let's go ahead and try that. This is where I'll be making your quiz questions from. So the website that we're going to look at is marksmath.org. So this is a professor at a California university. marksmath.org/visualization. I think it's a /, isn't it? /Julia_sets. Okay, marksmath.org/visualization/Julia_sets. And this is a very nice generator. You can click on, see, here's the Mandelbrot set, and you can click on any point in there, and if you click on the black point, so this Mandelbrot set is sketched in the complex plane. The x and y axes are not drawn in. If they were drawn in, the origin would be right. Where's my cursor? The origin would be right about here. So the y-axis would go here, and the x-axis would go here. Or actually, the axis with no eyes would go here, and the imaginary axis with eyes would go here. At any rate, you can click on any point. If you click on the black, then you get a connected Julia set. So the sphere on the right is the Julia set that goes with this point that I clicked on. So this is all filled in black. Everything in here is connected because I picked a point that's nice and clearly in the black. And so the point is identified right here, -0.047 minus 0.07i is in the Mandelbrot set, and so the Julia set is connected. Now you can clear that out. Make sure you clear out each time. And if you pick one out here that's clearly not, I don't know what I just did. You pick a point out here that's clearly not in the Mandelbrot set, you get a scattered Julia set. So the 0.13 minus 0.77i is not in the Mandelbrot set, and so its associated Julia set is disconnected. It's a bunch of scattered points. So this marksmath.org doesn't have all those colors, which look beautiful, that make it a little hard to see what points are actually in the sets, because just the black points are in the sets. So clear that out, okay? So I'm going to click right here. See where my cursor is? Will I get a connected Julia set or a disconnected Julia set? Connected, right. So I'm clearly right in there, and so you see it is in fact connected. Okay, now I'm going to click over here. Will I get a connected Julia set or disconnected Julia set? Disconnected, yeah. And you see it's disconnected. The more interesting points are right around the edges. Then it's kind of hard to tell if they're right in the Mandelbrot set or if they're not right in the Mandelbrot set. So on a quiz, I would give you the two pictures and ask you, did the Julia set come from a point in the Mandelbrot set, or was the point that goes with this Julia set not in the Mandelbrot set? Okay, because every Julia set, every point in the complex plane has a Julia set. And so I would just ask you from the image if you can tell. So from this image, did this point come from a Julia, was the point that goes with this Julia set in the Mandelbrot set? Yes or no? Yeah, it was. It's connected, so that's why it was. Okay. Anybody want to try some more examples on here? So you can experiment there, okay, and make sure you understand which images are from points that are in the Mandelbrot set and which images are from points that are not in the Mandelbrot set. Or you can just make a fancy screensaver. Okay. Well, we're going to go on to section 8.1, so hopefully you all brought your cards. I should show you the life lesson from section 7.4 before we do that. So 7.4, we saw Mandelbrot taking Julia's work and proceeding on with it, and that's exactly what the life lesson is. Visualize the same idea in different ways to see relationships. So 50 years after Julia came up with his fractals, Mandelbrot made another fractal from that. Chapter 8 is on probability. So probability is one of the triumphs of the mathematician. We're taking something that we don't know what's going to happen, and we're able to figure out enough information to make it useful, even though we have no idea what's going to happen. For example, have any of you been to the casino? I guess you can go to the one in Michigan if you're 18. But anybody ever go to a casino? Yeah, okay. So who thinks the casinos are making money? Right, yes, the casinos are making money. But do you know when you go in the casino if you're going to make money? No. Does the casino know when you come in if you're going to make money? No, they don't know. And yet they have enough information from probability to still be making money. Same thing with insurance companies. Insurance companies don't know if you're going to get in a car accident. You don't know if you're going to get in a car accident, although you have more control than the insurance company. Unless that deer jumps out in front of you, okay? But the insurance companies, who thinks the insurance companies are making money? Yes, insurance companies are making money because even though they don't know, they have enough information that can help them still figure out how to make money. So that's from probability, and we're going to look at that in Chapter 8. First, we'll look at a scenario. So this is the reunion scene, take 1. Suppose we return to our 25th college reunion and we see an old classmate. Classmate, I have 2 children. We, wonderful. Is the older one a boy? Classmate, yes. And? At this point, she chokes on an hors d'oeuvre and collapses. Oh no. Suppose we return to our 25th college reunion for take 2 and we see an old classmate. Classmate, I have 2 children. We, wonderful. Is at least one of them a boy? Classmate, yes. And? At this point, she chokes on an hors d'oeuvre and collapses. Okay, what's the difference? Anybody catch the difference between the 2 scenarios? They're almost alike.
Is the older one a boy versus is at least one of them?
Is the older one a boy versus at least one a boy? That's right. So naturally, we have some concern for the respiratory challenges of our former classmate. However, we probably would be more consumed with the following burning question. What is the chance that our classmate has 2 boys? Is the probability the same in both scenarios? Well, let's go ahead and write those down, those 2 scenarios down, and I'm going to ask you to predict what the probability is in the 2 scenarios. First, I need a cough drop. Has anybody ever discovered Sucrets? Man, those are like the cough drop of cough drops. Excuse me. Excuse me. Okay, so is the older a boy? Yes. What is the probability that both are boys? Go ahead and write down your prediction. Is at least one a boy? Yes. What is the probability that both are boys? So we're going to have you write down that prediction, and then we're going to simulate the situation by taking your deck of cards. If you do not have a deck of cards, please go online. There's deck dealers. One of the students had one, deckdealer.org or something. She dealt a deck of cards there. Okay, so take out your cards and shuffle them. Or find, is it deckdealer.org? Something like that. Did anybody find a website yet? We'll share it when you do. Okay, so this is, if you didn't bring a deck of cards, you're going to need a photo of doing this, so you'll have to do this later on your own. We're going to simulate having pairs of children. So the cards will be dealt in sets of 2, and you'll need one lower and one higher, because then the lower one is the firstborn. So here my 6 is the firstborn, and my 8 is the secondborn. So the lower card is the firstborn, and the red ones are girls, and the black ones are boys. So, excuse me, having decks of cards where the red cards are girls and the black cards are boys is a good simulation, because the same probability of getting a red card is the same probability of getting a girl. Excuse me. So deal all your cards out. So you might need a little more space. Deal all your cards out. Okay. And then I'm going to come around and help you figure out how many are girls and how many boys. Did anybody find a website yet that will deal your deck out? If you do, raise your hand. I'll come and get the site name. Someone had it in the first class. Maybe I could find it on mine.
Deck of cards.
Deckofcards.org?
Yeah, or it says HTML5. I don't know if we're...
Deckofcards.org, HTML. Maybe if they search on deckofcards.org, maybe that'll come up. Thank you. Once you get your cards dealt out, then I'm going to show you how to tally them up. Where did my notebook go? Here it is. So once you get your cards dealt out, then tally them up by figuring out which cards, both cards are black. Then the bottom is black and the top is red. The bottom is red and the top is black. Okay, so that's what I'm going to ask you to count. We don't care about the sets that are both red, because those are where both are girls. And the classmate told us that either the older one was a boy or at least one was a boy. So we don't have any sets that we're interested in where both are girls. So this is simulating a whole lot of different families with 2 children. So 26 for each of you. Once you've gotten yours tallied, I'm going to come around and write the numbers down so we can add them up as a class. And we'll get some evidence to support what the probability should be for each of the two scenarios. The only drawback about Sucrets cough drops is they put your tongue to sleep. Yeah. When you have yours added up, let me know. I'm going to come and write down your amount.
Do you count the ones that are both black as also having a black bottom?
No, the ones that are, if you counted them because they're both black, then don't put them in either of these other ones. Okay, so this, if you get done ahead of us, this is your class activity, so you can upload it. Were you able to deal out pairs on the screen then?
No,
No? Okay.
it's be manual.
Okay. Okay. Did you get your screen? Yeah. Okay, so you have both black, you have 7. And then the bottom black and the top red.
Yeah, 11.
And the bottom red and the top black.
1.
Okay, did you find some online? Yeah. Oh, good job. What was the website? Okay. Okay, good. So when you get your tallies, let me know. You have yours? Okay, what do you have there? So both are black. Is that 11 or 2? 11? Okay. And then 2 where the bottom black and the top is red. And none where the bottom was red. Okay. And how about yours? What did you have?
I have 7 all black, 7 bottom black, and 4 bottom red.
Okay. Okay, that's a nice check to make sure. Okay, so 4. Okay, and then did you get yours down?
Yeah.
Did you want our tallies? Yes. Are you still Are you still telling me?
So I can see a screen for some of
Okay, did you get any tallies?
We're counting it right now.
Who else do I have? Who else has a tally I have not collected?
I watched Marvel Avengers Endgames yesterday,
Okay.
and they had the Mobius band. And
They did actually. I
What-
saw it too.
What was it? Marvel Avengers?
The
Endgame,
Endgame one.
the last one that just came out.
Yeah, I saw it too. I didn't watch for it. I should have paid better
Because when
attention.
he was on
Oh,
Tony's.
don't spoil it.
I think I saw it though. Did it just?
It just came out
Oh, then
today.
Movies.
Today?
Yesterday.
Oh,
Well, yesterday.
Okay. Oh, good.
I sat there and elbowed my mom's like, yes, man.
Yeah. So the
He
movie
said it
was in
wrong.
there, so watch
Okay.
for it.
I will.
But don't spoil it.
Thank you. Okay, so everybody's collecting their tallies and getting them together. Just a few more to go. Okay, what do you have?
For like the red one on the bottom and the black one on top, 4. Blacks was 6, and then black then red was 10.
Okay, thank you. We work together.
Yep.
Okay, so I'm going to ask front row to add these up, middle row to add these up, and back row to add these up. So we're getting some data to help us ascertain what this probability should be. So add up all of these numbers together, okay? And this will represent lots and lots of families with 2 children. Once you've added them up, ask the person next to you so we have some backup data, okay? So we can confirm.
The middle is 54.
54, you both got that?
Yeah.
Okay, great. 54. Front row. What did you get in the front? Nobody added in the front? Okay, add in the front. Back row, what did you get? Didn't know yet?
45.
45? Anybody else get 45? Still working? Well, try again. We just need 2 people to get the same number.
For the top row, is that a 7 after the 4?
That might be the problem. Yeah, that is a 7. Yes.
Okay. I got 50 for the top row.
You got 50? Anybody else get 50 in the top row? Okay, 50.
Yeah, I got 50.
Okay, bottom row. Are we coming up with any numbers here for the bottom?
Are those both 7?
Yes.
45. Yeah, we got 45.
All right, that's the concurrent. So this represents all of these families. How many with families all together? Thank you for adding these all up. 149 families all together. And so the ones that had, is the older a boy? So the ones that had, is the older a boy, this one would have answered, and this one. The bottom was the older child. So the first 2 would have answered to being, is the older a boy? The 50 plus the 54. Is at least one a boy? Is at least one a boy? So that would be, yeah, wait. Yeah, is at least one a boy. Okay, all of them, 149. Okay, so we have the older one a boy, at least one a boy, and now out of those, how many were both boys? So 50 out of 50 out of 104. Or 50 out of 149. So you would have thought that they were both 50%, but it turns out that's not the case. This one is the older boy is in fact 50% probability, but is the 1.5. But in the one is at least one a boy, that's actually not a 50% probability. It's only a 1 in 3 probability. So 0.34, 0.33. So our experiment carried out what we see in the probability. So we're going to see in section 8.2, well, how come in the one case you get a 50% 0.5 probability, and in the other case only a 1 in 3 probability? That doesn't seem right. It seems like they should both be the same. So hopefully that's a cliffhanger. Our section has a life lesson today It's thinking about situations that jar our intuition can lead to new and important insights, and we'll see that in 8.2 on Monday. Have a great weekend.